we're really honored to have today with us Ioannis Tsamardinos. Thank you, Ioannis, who will be talking to us about a very interesting endeavor that he has started in the last few years to bring machine learning into biological problems. Thank you for being with us, and the floor is yours.
Thank you. Excellent. Okay, first of all, let me really thank the host for inviting me. It's a great opportunity, and I'm very excited to be here. I can see in the audience some very esteemed colleagues and friends. So I'll be glad to take your questions after the talk and have some discussions. I'll be discussing the automated machine learning efforts that we have, what it is and the problems that it solves, and particularly how we constructed a commercial platform called JADBio or JADBio, employing our research all of these years into the product. Of course, I need to declare there's a conflict of interest as these algorithms are being commercially exploited. Keep this in mind. And essentially, I'll be presenting technically, at least on the technical part, how 20 years of research in various aspects of AI, like feature selection and machine learning knowledge representation, meta-level learning, statistical estimation techniques, and others, actually become a commercial product. So in business, it's very good, it's necessary, I think, to start with the need that your intended users and clients have, and what is their problem in solving this need. So an oncology has, for example, the need or a problem to predict which patients will get cancer. A pharmacologist may want to discover, meaning predict, which drug is the most effective for treating the disease they study. A biotechnologist would like to learn how to predict what affects the quality of the crops. And for technical people, we realize these users, these clients, potential clients, need machine learning. That's what solves these problems and many, many other similar problems in life sciences and the industry in general. But what is their problem? The problem is that machine learning is inaccessible. It requires people with deep expertise, like PhDs and industry experience, and they are scarce to hire. And even if you do find them, they often, it's easy to make a mistake and have models that they give the wrong predictions. And in life science, the wrong prediction may mean you kill a person or you maim them. It requires coding and software engineering, and that means it's inaccessible to the known coders. And life scientists are usually known coders, which means they only have access to the knowledge in their data through the data scientists, and they have to mediate the discovery. So that means lost opportunities, time lost, and perhaps misinterpretations. And that's why the statistics tell us that only 0.5% of the data produced are ever analyzed, not analyzed correctly or optimally even, just analyzed. All right, so this is a problem, and what we propose as a solution is automated machine learning, which is what I'm going to describe next. And of course, technically how you build something like that. So the mission in all of these problems, it's something that's in general difficult. We want to create a predictive model, meaning we look at the past and the recorded data of, let's say, molecular profiles or profiles in general, and some outcome that we care about, some quantity that we care about. And we want to learn a predictive model that, of course, is predictive for new unseen profiles. So in life sciences, these profiles are usually transcriptomics, proteomics, and all sorts of different omics and combinations, multi-omics. Could be genetic, could be clinical and medical quantities that we measure. It could be even that we take images of people and want to use them to predict or classify, and combinations. And typical outcomes of interest is could be disease diagnosis, disease status, or subtype of the disease, a phenotypic trait, and time to some event of interest, like death or metastasis or relapse of disease. Of course, this is in life sciences. In the industry, it could be like we have the profiles. You can think of them as like, for example, the profile of a contract could be some characteristics of a contract, and we want to, the outcome of interest could be when a person is going to like stop their contract. But this is not the whole deal, because like life scientists don't only care for the predictive model, they care to discover knowledge. And they'll come and ask you, what are the quantities that actually, out of everything that we measure, that are jointly predictive of the outcome? And even if we solve these two, we also need to deliver a quality assurance on the model, meaning how predictive it is before we actually start using it. So this is why we want to automate. And as a specific example, I have here like the data taken from this publication in 2013, where they measure like in 70 subjects, some with Alzheimer's, some without, corresponding to a row in this Excel file. They measure like 503 different molecules that are called microRNA molecules in the blood. So we have 503 columns of predictors, and the outcome is in the first column here. And you can think of your data as like as a big Excel file. So now what? Now, how do we solve our problems? Well, if you're like an analyst, an experienced analyst, you would like script your solution. What we are doing is like build the system that automatically like solves and analyzes not just this Excel file and data set, but any similar, whether it's like big, small, and so forth. So the field is called like AutoML. It's rising, not only like commercially, but it's rising like in the academia. There are lots of papers and algorithms published solving problems in automation. And our system is called JADBio, which is specifically designed for biomedical data. What is specific in this type of data? Well, you may often have like very few samples because measurements are expensive, or you need to treat like samples with different like drugs, and this is difficult. And they measure also hundreds of thousands of features, sometimes millions of features. So we can break down like our design choices and how we build the architecture in 4 steps. Step number 1, how do we decide out of the hundreds of machine learning algorithms out there, which one to use and how to combine them, which essentially machine learning pipelines to try. And I'm going to be using the term configuration for a machine learning pipeline. So these are options to construct like models. And then we need to determine which one's the best one, which one wins and produces the best models on average. How we build the final model and how we estimate its performance. And somewhere in there, like we also need to consider that we want to like solve the feature selection problem. And also how we use images as predictors, which in this talk, I'm not going to go for into that for time purposes. All right, step number 1, how do we determine the set of options? I have here like the steps in the pipeline in a configuration, like pre-processing the data and selecting the features and then feeding them to a modeling algorithm, machine learning algorithm. But there may be like steps for imputation and feature extraction and transformation. So it could be more complicated. And there are hundreds of choices for each step. Which one should I try? Not everything can be applied on your data, on the next data set of the client. Some only apply like in, when you have a lot of samples, some only when you have like few samples and so forth. On top of that, like to make things worse, for each algorithm, we have lots of choices for their hyperparameters. All algorithms accept some parameters that are called hyperparameters, and they determine the behavior of this algorithm. Usually they make them more sensitive in identifying patterns or less sensitive. And if you don't tune them right, you don't get good results. So which values should we try? When you instantiate all of your choices for the algorithms and the hyperparameter values, that I call the configuration. It's a pipeline with all the choices instantiated, and it takes you from the data to some predictive model instance. And when you consider them all together, this is the configuration space, everything that you could try. And in this example, I have a portion of the configuration space, just 5 of them. In each row, there's a pipeline. We see here like this, apply this preprocessing, then this feature selection with this hyperparameters, then this like classification algorithm and so forth, coming from JADBio. So in order to select like out of like many choices, we represent the knowledge in a good old-fashioned AI ontology system. So AI is not just deep learning, it also includes like knowledge representation. And we use them like to essentially encode the knowledge of a statistician. And so we can then ask a question, what a statistician, what an expert analyst would do in a situation like that. And on top of this ontology, we define the rules that determine like the algorithms and the hyperparameters that we should try. However, this jumpstarts the system with some knowledge, but of course, we're not perfect. We don't know all the knowledge. So then we have a mechanism to induce and learn new knowledge. The way we do that is we record from every user and every client the results of their analysis. So for example, that we analyze the data set with this number of samples and this number of features and some other characteristics that are called meta features. And we tried these algorithms and we got these performances. So then we can apply machine learning on the results of machine learning. That's why it's called meta-level learning or meta learning, and induce new models and new rules and new knowledge about when to apply an algorithm, in which situation to apply an algorithm and expect good results. So we use both of these like solutions in JADBio, and that makes JADBio a self-improving system. Okay, next step in the designing the architecture is now we have laid down all our choices. How do we choose among them and optimize? So specifically, how do we estimate how good is a configuration? Meaning like on average, how good like models it produces. And if we can do that reliably, we can choose with high probability the best configuration for our problem, the best pipeline. And secondly, how we intelligently search in the space of all these configurations. So let's see how we can evaluate a single configuration. We use, and I think everybody else is using, what is called out-of-sample estimation protocols, meaning algorithms that leave out a portion of the data for testing and estimating performance and some of your data for training. So we train a configuration on the trained data and check how well it predicts unseen new test data. And this way we get an idea of the quality of this configuration on our specific problem. If we do it just once, this is called holdout. If we do it many times in a certain way, this is called cross-validation. But however, if we want to automate the procedure, we need to decide automatically how big this test should be, how many times we should repeat the procedure, and so forth. And these decisions are give very different results depending on whether you have like small data sample sizes, big sample sizes, lots of classes in your classification problem, and the like. And unfortunately, there's very little guidance in the literature about how to do that. But we have like, I'm going to skip the technical details. It suffices to say that we have put in our AI system in JADBio how we select like which protocol to run based on several factors like the total sample size and how imbalanced are the classes that we try to predict and the preference of the user for how much computational time to spend and the like. So that was an important problem to solve to automate things. Okay, and now we have a way of, we have laid down all our options, our configurations, and our estimation protocol to figure out which one's the best. How do we select a search to find the best? We do the simple thing, which is try all configurations. This is called the grid search, but we do have some smart, I hope, like intelligent rules to avoid unnecessary computations. The first rule is like when we perform a statistical test, and when as soon as we realize that a configuration is with very high probability not going to be the winning one, we drop it. We don't keep like doing any computations involving that configuration, and that saves computational time. And also, when we see that our cross-validation procedure doesn't reduce our uncertainty in our estimation and how good like the model is, the final model, we stop like the process and just return the results up to that point. Okay, now it's also important, up to now, if you noticed, I always refer to configurations as one thing, not individual like steps like imputation or feature selection and the like. Now that's because it's very important to treat them as atoms. All of the steps of the analysis need to be cross-validated as one thing. You don't first do the imputation, then you run everything else. You don't first do the feature selection, then you do the cross-validations. Or you're doomed to have like severe mistakes in your analysis. I'm not going to say more, just refer you to this like experiment in this book, and I'm sure it will catch your attention. The previous note is important to ensure correctness of estimation, and that, of course, is important in life sciences. Okay, so how do we produce a final model? Well, we use the winning configuration, but on all available data. And this is going to lead to the final model and the final selection of features. And this way, we avoid a big problem, which is we don't lose samples to estimation, as it's called in statistics. We don't have a holdout set to like estimate the performance of the final model. The final model is built on all of our data, but we have already estimated, we have already done some estimations by training on subsets of the data with different configurations. All these other models are built for estimation purposes only. And if you notice, that's a big perspective shift, a subtle point, but it's very important. We don't estimate the performance of the final model. We have not left any held out data. Instead, what we do is estimate the performance of the configuration, of the pipeline, of the procedure that produces the final model. This is quite important if you want to apply AutoML on small sample data. And this is very common. Small sample data is very common, like in life sciences. I think 70% or more of the data sets in the gene expression omnibus have fewer than 100 samples. All right, so now we have our final model. We have figured out our winning configuration by estimating the performances of all configurations and selecting the winning one. What's the estimate of the final model? How do we estimate the performance of the final model? But wait a minute, didn't we just estimated the configuration that produces it? Can we just return that? So for example, if the best configuration gives a model with accuracy 90% out of all the ones that I tried, can I just return 90%, right? The answer is no, unfortunately. That's what Einstein says. No, actually, Einstein didn't say that, but David Jensen said that, like back in '92, and also in statistics, they named this phenomenon winner's curse. What they say is that the cross-validated estimate of the best configuration is actually optimistic. it's you may think it's 90%, you may estimate it as 90%, but it may be like 50%. Okay, let's see why. Let's see an example. All right. When I try one algorithm and one hyperparameter, one configuration, and I simulate it to have accuracy of 85%, and I apply it on a test set of 50 samples, and I estimate like the accuracy at 90% because I was a little lucky on this specific 50 samples. Now, if I were to try the second time, I may find 70% accuracy. I was a little unlucky. And a third time, 87%, and so forth. Of course, in practice, I only have one test set or one data set. But here's a simulation, so I can see what happens on average. And I simulated like 1,000 times, and I see that on average, the average of this histogram of all the simulations, I estimate performance and accuracy at 84.9, which is very close to the true one, with some uncertainty, with some variance. That's what happens when you have one configuration, one pipeline. But nobody tries one pipeline. If you're an analyst, you're going to try a few at least. If you're not an ML system, you're going to try thousands. So let's see what happens when you try 8 of them, just 8. Okay, so here's different algorithms like decision trees, simple Bayes with different hyperparameters. I assume all of them, I simulate all of them to have the same accuracy. But when I try them on a test set, one of them is going to be the winner because it's a little lucky on this specific data set. But if I were to do it again, maybe I would have another winner and another accuracy estimation of the winner and so forth. And this is what happens when you do it like 1,000 times. On average, your estimate is optimistic. You report 0.91, while the true one is 0.85. And if you had thousands, it may be even worse. And if you have few samples only, it may be even worse. So we got to do something about that. And what we do is we invented a statistical procedure called bootstrap bias correction, or bootstrap bias corrected cross-validation, that removes this estimation due to multiple tries. And this is fundamental for life science small sample data. All right. Now, as I said, like predictive modeling is only part of the story. The other part is knowledge discovery. So a doctor, for example, may not care about your wonderful diagnostic model. They can do the diagnosis themselves sometimes. But what they care about is what is diagnostic, the quantities, the features that you measure or they measure that are actually diagnostic. And this is, so it's often the primary task in many applications. So how do we define feature selection? We define it as follows. We seek to find a minimal set of features, minimal size set of features, as small as possible, that is, that collectively, meaning like not when you look at one by one these features, but jointly, combinatorially, they carry all the information for optimal prediction. So considering only them doesn't lose any information, you still get the best model possible. So for example, if you have like a data set like that, and this is the outcome here, whether the tumor is metastatic or not, based on these features that are names given by Affymetrix and the measuring technology, doesn't really matter. We may end up with feature selection, figuring out that just these two quantities are sufficient to optimally predict the outcome and diagnose the outcome. And that's great and suffices for predictive modeling. But when you do this for knowledge discovery, it's misleading. It is misleading because it may very well be that there's another set of two features that also carries all the information for optimal prediction. And there are very, very few algorithms that actually report multiple solutions to the feature selection problem and solve what we call multiple feature selection. So very few algorithms, I would count them like on my 5 fingers, probably. All right, but we have done like lots of work in feature selection. First of all, to scale it up to possibly tens of millions of features. And you may think like, is this like actually practical? I mean, are the data sets with millions of features? The answer is yes. I was talking like the Hunt Institute, and they're measuring like 30 million genetic markers. And they try to like predict like propensity to diseases based on that. On the other extreme, and they scale also to very large sample sizes. On the other extreme, we need algorithms that scale to very few samples when samples are hard to come by. For example, we have a rare cancer, and they consider any type of outcome, and they identify multiple solutions. And you can find a lot of them actually in open source R package called MXM. And here's actually a list of the most important ones that we have invented for different situations: small sample size or big sample size, when you want to identify one solution or you really care about many solutions, and so forth. And this, of course, have been embedded, some of them like into JADBio. So putting everything together now, let's see how we design the system. We start from a data matrix and the user preferences, maybe like about how much computation to use, for example. This is the outcome. And what we do next is the AI system needs to determine which algorithms to run and which combinations are allowed, and which hyperparameter values are allowed for this specific data set. And also the AI system, using also the Metalevel learning system that induces knowledge, determines which estimation protocol is better. Is tenfold cross-validation the best, or a single holdout, or something different? And then the configuration generator generates all these pipelines and starts trying them. So we have different configurations with steps like preprocessing, transformations, imputation, feature selection, and finally modeling. And we feed these pipelines into the estimation protocol, let's say cross-validation. We try them all. Let's not forget, we also have these heuristics to stop computations early. And we gather, we'll see why, the predictions stemming from the models of these configurations on the test sets. Okay, so based on these predictions, we can figure out which one, on average, is more accurately predicting of the outcome on new unseen like patients. And we can choose the best, the winning one. And then based on this winning one, we can run it on all the data, so we don't lose any samples to estimation. And that produces our final model and our final feature selection. And then we also feed these predictions to our bootstrap bias correction protocol to get an unbiased, accurate performance estimate of this final model. All right. And that's perhaps, that perhaps would be the end of the story. If we were to roll this out as a, let's say, an application, but turning into a business, it's a whole new story. So first of all, you need a good team. And I was very, very lucky, like to have a good team like in place, or at least like acquired one for some positions like over the years, with our founders here, and also like Kenneth is our Danish like associate, and Aris is our chief business officer in Silicon Valley. Maria is like our CFO, and so forth. We have around like 13 people full-time, plus like around 7 people like part-time and freelancers. Now, technically, JADBio is a software as a service that runs on AWS cloud. It has a microservice architecture using Kubernetes. We build most of all the algorithms from scratch in optimized implementations in Java. But we have the mechanisms to link to any external libraries in other languages when we need to. And the AI systems is built on OWL and some rule reasoner, which I forget the name. And we also do a lot of research in prototyping languages. The results are produced in JSON and jar files, so they can be used like and interoperate with other systems. Now, the advantages, I hope that will become obvious once you use the system, is you really boost the productivity, and you can do in a few minutes an analysis that would have taken like weeks or months of scripting and testing. It democratizes to people who don't know math and they can't code. And I'm very proud when I see, I feel very proud when I see our system being used by biologists or clinicians. And they publish like in the best journals sometimes with our tool. Also, correctness is very important. You cannot mislead your clients. You need to be able to tell them like a correct estimate of their predictive performance. And the quality is often beats like the human experts. As one example, we got like 3rd place in a recent Food and Drug Administration prediction challenge. Okay, and you need something like that before or you get any investment. Actually, you need to map the landscape. So there are many competitors, direct competitors, and there are many alternative products. But if you map them in these two axes, how much expertise is required to do an analysis? Can you do it even if you have no machine learning knowledge? And how much like specific they are, and they can run on molecular data? I think we covered like a gap in a niche market in the market. Also, the use of partnerships is very important to accelerate growth in a product. So you need like business developers that seek and get you this like partnerships that make sense commercially. Indiviumed is our strategic partner and investor, and they use like JADBio in their AI platform called Unravel. QIAGEN is a giant in biotechnology, worth $9 billion, I think, and we have like a global distribution agreement now that we're making our products interoperable, and also other partnerships. The algorithms and research going into JADBio is getting now around 1,000 citations per year scientifically, and we have like 36 discoveries using JADBio. Here you can see one on COVID, a recent one in the Nature's scientific report, but also in less, let's say, molecular applications like predicting post-traumatic syndrome disorder in war veterans. This was work done with the Danish Veterans Center, or predicting crop quality in potatoes and so forth. This is a list of affiliations of some of our clients. And actually this Saturday, we got like a Spin-off of the Year award by the Ministry of Development Investment and their organization for innovation called Elevate Greece. We thank them very much. Some of the lessons learned, like building this. Okay, first of all, like to summarize, JADBio automates predictive modeling and knowledge discovery with an emphasis on the life sciences, of course, and molecular data. And incorporates numerous research results and innovations in AI and ML that were fed and still feed into the commercial product. A commercial product is not just research, and it's not just development. And I'm learning the hard way. It requires you to do proper versioning of your code and maintenance of the system. And you know, if you have a lot of clients, you need to be backward compatible. when you do research and you find, for example, a new algorithm is good or bad, you need mechanisms to disseminate this knowledge within the company, so you don't keep reinventing the wheel. You need to maintain the documentation and so forth. There are like so many things that you need to take care of before you actually like roll the product out. Legal issues, privacy, security, and so forth. Business development and sales is king. And I wish I knew that like, or realized it as strongly earlier. So you got to like partner up with good like business people like early on. You may have an inferior product. You have a business developer and a salesperson that is good, like you may dwarf the competition, and vice versa. You need to know your customers, what they're looking for, their needs, how they make decisions, what they're willing to pay, and all of that stuff. Now, in terms of like collaborating, please try our free version. Contact us for any ideas you may have, projects you may want to run. And also we often hire, so we'd be like very happy to receive like applications if you're looking for a job, even though like I don't think we'll be hiring for the next few months. So this is where you can try it out and test it out. And you can follow us on the social media. If you want to see technically how it's built and validated, there's a preprint that you can look at and so forth. I would like to show you like a live demo where you can see a lot of information, but you get access to the application through the login. And once you log in, you get to see the dashboard. Let me add some data. I went to an existing project, upload the file. So now I'm going to drag and drop and upload the this one, the Excel file that I mentioned with the Alzheimer's. Okay. I'm going to go through this quickly, like the uploading phase. I'm just indicating here that I have a header with the feature names and a header with the sample names, and I give it a name. Let's see this one. Okay, and here you need to annotate, like we automatically annotate whether a column is categorical or numerical. We give the option to the user to change that, but I'll skip it because it's correct. And now I can see the data set. It has 504 columns. The first one is the diagnosis. If I scroll down, I'll start seeing like the controls. And I have some Alzheimer's. And here are like the different columns, like for the microRNAs. And I can scroll and see the rest. And now let's do an analysis. So analyze data. I indicate that I want to create a classification model for diagnosis, given the other measurements. Next, I indicate that I want to enforce feature selection, give it like, let's say, do a typical analysis, not a quick one or an extensive one. Give it like a few cores to run, and then run the analysis. And now it goes into our servers, and we can progress the monitor the progress. So here the system has set out to fit and train like 120,000 models using like around, if I recall correctly, 3,000 configurations, and starts like trying them out, but it's going to stop like earlier due to this heuristics for saving like computation time that I mentioned. Here I get to see like the configuration, the steps that lead to the best performing model up to that time. And around 80,000 models is going to like stop. And here I get to see the current like best performance with the confidence intervals. Let me switch to some canned results so I can actually show you what you get out of this procedure. So I get like, this is something that I ran like a few minutes ago before the talk. And here this is the configuration that leads to the best model. The best model has this area under the curve, which is a metric of how well I can classify, I can diagnose patients or average precision with confidence intervals. Here I get to see the unadjusted estimate without adjusting for Wiener's curves with our bootstrap technique. This is the adjustment estimate. So this is actually an overestimation, overfitting estimate. Here I get the ROC curve. For those of you who know a little more technically, I can pick an operational point on the ROC curve and tune my false positive rate to achieve the best trade-off between false positive rate and best and true positive rate, depending on what is the best for the clinical application. I can also see like all other types of metrics. Feature selection. I'm informed that out of these 503 features, you just need 3 with these names to obtain optimal performance. Here with these plots called ice plots, you can gauge like the role of these features in the model. So I can see here that on average, the higher the values of this in the blood, the higher the probability that you have Alzheimer's. So this is actually a risk factor. And I can also see their feature importance, or let's see this one. This is the performance that you get if you use only the first top feature, the first 2, and the first 3. So if I use just the first one, I get 90% of my optimal performance. I can like visualize the data in 2 dimensions. Let me also show you just one last thing. You can apply the model and explore it, say the best performing one. You can apply it on a new data set that you upload, or you can download the model as an executable and incorporate in your software, or you can manually like fit in some, the analysis finished that I started before, or you can manually like plug in some values into the model, let's say 10,000 here, and run what if scenarios for, let's say, a new patient, and get like that someone with these measurements, according to the model, has a 92 probability of being a healthy person. All right, I'll stop here to allow like questions. Thank you very much for attending this.
Thank you, Ioannis. Thanks. This was a very interesting talk covering things from a wide spectrum, from basic science to the application and business. Thanks for bridging this in a very nice way. The first question asks whether you have applied that to applications outside the life sciences, and I believe you've already mentioned that this is the case.
Yes, absolutely. We have applied it in financial data. We have publications in prediction, published results on predicting which bank is going to collapse and go bankrupt in the next quarter, and also like fraudulent credit card transactions. We have applied it in material sciences and also in psychology. And yes, I mean, it's a general.
But business-wise, I guess.
Yeah, business-wise, like.
But business-wise, I guess
yes.
you focus on life science. Right?
Yes, that is true. We brand it for life sciences because that is a niche market with a huge gap in AutoML needs. And if we were branding it as a general tool, we would clash with giants in the field like H2O and Data Robot. So it's mostly for marketing and branding, but absolutely, yes, it could run like any type of data, as long as you have it like in a nice Excel file.
Yeah, but I think it is important to mention also the business aspects and stress the business aspects, that it's different. I mean, it's different to have a system that can be applied to many different problems and different to sell the system for many different problems, right? So one needs to bear that in mind.
Exactly. That's the key point. And what we realized in this effort is we have a system that can solve lots of different problems and be applied in many different sectors. And we have lots of ideas about the future and how to extend it and maybe go to other verticals. But when you present to clients and users, all of these possibilities and opportunities, they get confused. When you present them to investors and you say, well, I intend to also apply it in the insurance companies, and I intend to apply it in the, I don't know, material sciences and things like that, they get confused. And actually it's detrimental to your efforts to brand it and to raise money. It's detrimental. And sometimes you got to focus, even though your system and your product is applicable elsewhere, you have to, insist, this is what I'm going after.
Fully agree with that. Let's move to some more technical questions here. I see one of mine, I'll skip that. There is a question about handling data imbalance in classification problems. Do you want to say something about that?
Yeah, absolutely. So data imbalancing is a big issue that you have to consider. I didn't have it in the technical exposition. It's handled in at several points, several ways. So one is your estimation protocol needs to consider the imbalancing of your data. So maybe you have 1 million samples and you think I have enough samples to do just a simple holdout. But let's say you have two classes. If one of the classes is very rare, let's say 1 in 100,000 is positive, you may have 1 million samples, but you just have 10 positives. So you can't just do a holdout. Okay, you would need to do something more extensive. I would recommend a repeated stratified cross-validation. Okay, so this is one place where we handle that. The second place is when you train the classifiers, we give a weight to the classes that is inversely proportional to their prevalence in the data set. And also, we are going to incorporate in other places, during feature selection and in other algorithms.
Thank you. I see another question has just come in about the combination of semantic rules and ontologies with the machine learning aspects of
with a meta-level learning.
Specifically, the question says, can you say a few more words about how you combine semantic ontological guidelines for selection based on the data set with the machine learning learned ones?
Yes. Yeah, I think he means the ones we learn using meta-level learning. Yeah, so basically, at least for the moment, this is a huge area of research. Okay, how basically you induce new knowledge from using meta-level learning based on past results. There's a lot of research published when you try to pick a classifier, but not so much when you have a whole pipeline and you want to optimize the choices. So the way we do it right now is we have our knowledge encoded in the AI system semantically, and that gives you let's say, all of the appropriate choices. This encodes essentially the hard constraints, and then the meta-level learning encodes the soft constraints. You do some sort of ordering of all these choices and maybe further filtering out based on machine learning models. So we do it in these two steps, hard constraints first and then soft constraints, and order your configuration.
And I guess this also makes sense in terms of computation time, right?
That's right, yes. You got that. So basically the hard constraints, you try to take care of the cases that some combination of algorithms or combination of algorithms and hyperparameters will run forever, this specific data, and you want to, of course, exclude that. And then the soft constraints give you an ordering, which ones to try first, and maybe you try the first 100, 1,000 choices first, and you forgo the rest.
Since we talked about meta-level learning, I also have a question about that. I remember back in 1993, I started doing some work on that during my master's thesis, and then I quickly realized that this is an area that I would not be able to get a PhD on because because it was too unpredictable.
You were too early. Not enough data back then, and not
well, That's true. That's true. But I mean, there is a fundamental question here. You will never be able to get enough representative data sets, right? To make sure that what you meta learn is going to cover any new data set that you're going to be getting. How do you address that?
Correct. And okay, right now we don't really address it, but these are all like, as I said, there are many open problems in this line of research. Because why is that? Because right now, only very recently, we have like this AutoML systems, and we can explore their properties, and they raise this type of questions, right? So this is a continuum essentially, or at least that's how I see it. Before you start running, you need to select your algorithms, and then once you start running, you could keep refining and reordering your choices, let's say. So you run the first, like, let's say, few configurations, and then you may do a reordering of what you're going to try next based on the results of that. And you also have to have mechanisms that you drop and abort some of these pipelines if they're just taking too long and they're hogging the computational resources of your cloud. So these are all problems that are coming up. We started the system, it was working great for omics dataset, and then, but then invariably, like, clients will upload all sorts of weird data, and it's impossible to be prepared for all of them. So you gotta have the mechanisms that dynamically identify problems and handle them in a graceful and intelligent way. And I'm not saying we're there yet, but there's lots of things that we're building to address these things. Good topics for PhD, no doubt.
Thank you for that. There is a new question about whether you're using probabilistic graphical models for causal discovery.
Yes. Okay, so basically, let me go back. I wanted to build, my research was on probabilistic graphical models. That was my research on. And I want to build like a company that actually does causal discovery, automated causal discovery. But when I was talking to potential clients or investors, they wouldn't understand. They wouldn't understand the differences. They weren't clear. I felt it was too early. So actually what you see here is the first step, but in the back of my mind is like, I want to automate causal discovery and not just do predictive modeling. So we have experimented. We have actually applied it on real data sets. Particularly, for example, we did the contract with a service contract with Geico, which is the largest vehicle insurance company in the US, to build a causal model of what affects their clients' behavior. And our most recent paper in causal discovery is how you tune causal discovery algorithms. And that's the first step that in order to build automated machine learning for causal discovery. So, and by the way, in addition, the feature selection algorithms that we use are inspired by causal discovery and probabilistic graphical models. Our heuristics have been inspired by that, and the theoretical proofs of the algorithms are done using like probabilistic graphical models. So it's not an alternative way for identifying the causes of diseases. It's, I would say, it will be the principal way of identifying the causes of diseases. Right now, we do prediction modeling. We don't claim to identify causes.
Great. That was very, very informative. I don't see any questions from other people, so I'll ask you my questions. In Geo, I noticed that you're using Geo a lot. Do you get different data sets that target the same problem, right? Alzheimer's diagnosis, for instance.
Yes.
How difficult or how possible it is to combine these data sets in a common experiment?
That's a great question. So what we did is, actually, this is another piece of work that we've done academically, and I didn't touch upon. What we did is like created a data repository where we download GEO data sets, the raw data, the images as they come from the laser, and we pre-process them in a uniform way so that actually all the measurements are comparable to each other. And this is called BioDatum. So you can find over here like a few hundreds of a few thousand data sets that are uniformly pre-processed, and they have been semi-automatically annotated. So you can actually get like all the data sets that pertain to, let's say, cancer or a specific type of cancer or psychosis or whatever. This is one. And in other publications, what we've done is we developed a model from one, let's say, prostate cancer data set and applied it on another prostate cancer data set as external validation, or Alzheimer. And it actually works in many cases, showing that, yes, like models do transfer between like different data sets obtained by different labs and medical and biological procedures, perhaps, that they may have like a batch effects. So it actually works in many cases. What we're trying to do now in JADBio is when you try to apply your data, your model developed, let's say, from one study to some other study, which may have like systematic biases, to detect whether there are systematic biases and warn you that, look, you know, this external data set may not be appropriate for your model. The training data are different, like from the test external validation data that you're using. I don't know if this answered your question.
Absolutely. You covered upon many of the problems that I was thinking about. So I would like to thank you again. It was a great talk. Again, very nice bridging between academic work and business problems. Thank you for this, and all the best with your business side of the work, but also the academic side.
Thank you. Thank you. It was an absolute pleasure. Thank you very much for inviting me. And at the very least, you know, it's fun and creative and inspired a lot of like my research the recent years. If nothing else comes from it, like a lot of good research, I hope, stems from this endeavor. Thank you.
Bye-bye.